Hello, calculus fans. Let's say we have two planes. They're given by these equations. 2x minus y plus z equals 5, and x plus y minus z equals 1. Now these planes are not parallel. And by the way, how can we know that they're not parallel? Anyway, non-parallel planes will intersect in a line. Let's find parametric equations of this line. And while we're at it, let's go ahead and find the angle between these planes. Alright, we need a direction vector for the line. Now the line is parallel to both planes, and that means it's orthogonal to both normal vectors. So all we have to do is cross the normal vectors of the planes, and what we'll get is a direction vector of the line. Now the normal vectors that were given were -2, 1, 1 and 1, 1, -1. Those are the coefficients on the x, y, z in the planes that we started with. Okay, so we're going to cross n1 and n2, our normal vectors. Usual sort of operation, put these into a matrix, a third order determinant. Break it up into second order determinants. And we end up with the vector 0, 3, 3. Remember, what we've gotten here is a direction vector for the line. All right, now we need a point on the line. Any point. So what we're going to do is take our two equations of the planes and try to solve them, sort of as simultaneous equations. All right, what we have is a system of two equations and three unknowns. All right, let's see if we can work with this. Let's add the two sides of these equations. We get 3x equals 6 or x equals 2. Let's plug those back in. We get 4 minus y plus z equals 5 and 2 plus y minus z equals 1. Simplify a little bit and we get these two equations. So that tells us that y is equal to -1 plus z. Now, we're not told what z is, so z can be anything we want. If you've studied linear algebra, then you should recognize z as being like a free variable in solving the system. So let's just plug in z equals 0 and we'll get y equals -1. So here's a point on the line. 2, -1, 0. And you could verify that this is on the line by plugging this point back into both equations of the planes, and it should satisfy both equations. So now we have a direction vector and a point. And that's all you need to be able to write down parametric equations for the line. Should look like this. X equals 2. Really, you could think of this as x equals 2 plus 0t, y equals -1 plus 3t, and z equals 0 plus 3t. And the last thing we were asked for is the angle between the planes. What we can do is find the angle between the normal vectors. So we'll use our dot product formula to compute the angle between the two vectors. So theta is inverse cosine of n1 dot n2 divided by the lengths of n1 times n2. And if we work all this out, we end up with arc cosine of 0, which is pi over 2. And that tells us that these planes are actually orthogonal. The angle between them is a right angle. Okay, that's all for now.